Why edit genes? The genetic code, the language of the instruction manuals our bodies read from to build themselves, is full of bugs that haven't really quite evolved away. These cause aging and various diseases and disorders, including autoimmune diseases and cancers. If you've ever had eczema, if you've ever had diabetes, any such autoimmune problem, if you know anybody who has had cancer of any sort, really, the chances are there has been a genetic susceptibility at the least. The genetic code is how we can tell the body how to protect itself better from radiation damage, harsh environments, and those aforementioned diseases and cancers. And while we're at it, we could even develop morphological freedom from a genetic source. Why not? Before we move to the next page, a little shout out for this background photo. It was by Enzo Di Fabrizio. It was taken more than a decade ago, and just keep in mind how fuzzy that image is. That was taken using electron microscopy to show DNA. So we need intelligent life to use gene editing to improve health, decrease the costs of staying alive, adapt to extremes, and diversify through morphological freedom. These are all very essential applications for this technology as it develops, because with it we can bring about an evolution revolution. We can literally take evolution into our own hands and direct it at a much faster pace, but also in a more controlled manner than it has ever seen before. Certainly when it comes to any life forms as complex as the human body. But where do you get the tools for that? It does seem like a very advanced notion to be able to create these kinds of vectors. This is where Vulpine Labs comes in. I'm Atamanasa Kitsune, and here at Vulpine Labs we're working on the systems that are needed to produce exactly that. Our steps of research begin with the need for improved genetic reads, which we look to a completely first principles approach to designing how genes are read, and improved gene editing. Once again, we go back to first principles for how the actual edits are carried out as well. We need to consider every aspect of the body and how any gene edits are going to affect it. So for that, we are creating a system that will provide a whole body simulation, and that simulation will be based on your own genetic information, so that the simulation can actually accurately reproduce what would happen if you provide a particular gene edit to your body. It will also be designed to produce multi-compartmental vectors that allow you to create and carry multiple gene edits that are released in a specific sequence and are applied only when specific conditions are met. And those vectors can be designed in that simulation and tested in it before you then output them to a molecular bioforge. And we will also be providing these tools that are the modules of our whole body simulation system to researchers and scientists even before we've completed our software. Because each module, when complete, is going to be useful by itself to scientists and researchers to improve your workflows, to improve your bioinformatics research capacities and capabilities. And the molecular bioforge itself is what we call the geneticizer. Between it and the GESS Unified Editing Suite and SDK, which is our whole body simulation system, we will be solving genetic diseases, adapting ourselves to extreme environments in a manner that is in theory, less likely to mess it all up than terraforming. Consider the difference between causing a mistake in one person and a mistake in one planet, particularly if it's already an inhabited planet. We can improve our efficiency as beings, as living biological bodies, and we can reduce our impact from food to clothes to transport. Meanwhile, we can make sure that we're putting civilization's metaphorical genetic eggs in more baskets. Because of this ability to adapt ourselves, we will be able more easily to take people to new places out there in the cosmos. And self-actualization, and a key concept of freedom of form, morphological freedom, will be absolutely essential to making sure that that adaptability is not only done for the sake of being able to survive out there, but also being able to enjoy and express ourselves. So the GESS, Unified Editing Suite and SDK, is our system of software by which we will achieve that simulation of the body, from which can be output the gene edits necessary. The 27 modules that we have so far designed for that system will each be coded and made available in our GitLab. 522 submodules, each representing a program of the same sort of scale as any tool you can run on your computer in bioinformatics today, will be networked together in a manner represented by the chord diagram in the background behind the GESS logo on this screen. As you can see, it is not a simple matter, but it is going to be worth it. We consider it to be of a similar complexity to developing an operating system for a computer. Meanwhile, the Geneticizer is our molecular bioforge device, seen here in one of the early prototype design images. We are currently working on further designs and improvements to develop the Geneticizer. There is documentation available on our PubPub website for you to see what our current iteration of research is like. All of our developments are open source. Our technological development strategy is based on the notion of running parallel to and eventually merging with the development of technologies in existing industries, and doing so in a manner that puts us ahead of the existing companies and other players in those industries. We have assessed that if one attempts to aim to meet current technology at its current level of development, then by the time you actually get there it will be old news. If one tries applying a fresh startup mentality initially, but then becomes a bit too focused on just reaching the trajectory of the other tech being developed, of trying to fit in and do the same thing eventually, as those pharmaceutical companies or other industries are trying to do, then while you'll not be so far behind, you're still going to be moving too slow. Successful endeavours may have a longer lead time to completion, but when they intercept other technologies' developmental trajectories, they keep up. Because we develop with a long lead time, but a big advantage over the existing paradigms to have a strong momentum to maintain our lead by aiming to intercept the future, not the present. So, our approach to research that keeps us ahead is Zarathustra. The Zarathustra philosophy is how we drive our approach to scientific endeavour, using engineering first. We go beyond where most scientists would dare to ponder, to find the islands of possibility, and connect them to the mainland of the mundane by building bridges of working engineering. This is in contrast to what a lot of scientists do, which is to stay where they are more comfortable on the peninsula of empiricism, connected to the mainland of the mundane by the isthmus of science communication. And they try to extend the peninsula of empiricism via the rocks of hypothesis and with consideration of the sandbars of conjecture. The downside of this is that they are only looking at things from a perspective of where they already are. So by going out into the sea of impossibility and finding the islands of possibility, and then building our bridges of engineering back from them, we may be taking risks, but we are doing so in a manner that still achieves big advancements a lot faster than your regular scientific approach can. These risks may look high, but we have an intuitive methodology at Vulpine Labs for finding these islands of possibility. This is borne out in the plans that we have built up that already extend decades into the future based on the trajectories of the technologies we are developing, and which we have already stuck to for the last 15 years without any real issues, without any major problems with what we're developing. We remain flexible. We adjust what we're developing to fit with the things that we learn along the way. And by applying that to our concepts and our ideas that we've planned out for those decades, we have a vast innovation power for our size. We have bold and confident ideas for novel projects, and we think outside of the box to get there. Our would-be rivals don't necessarily get it, but basically it's much like Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. And the corollaries that came with that from Barry Game, any technology distinguishable from magic is insufficiently advanced. And from Florence Ambrose, any technology, no matter how primitive, is magic to those who don't understand it. And our favourite, which came from the Girl Genius webcomic, Agatha Heterodyne saying, any sufficiently analysed magic is indistinguishable from science. Please, if you'd like to see where this attitude and this approach is taking us, check out our latest work. We are developing open source software in the form of the GESS. That's available at gitlab.vulpinedesigns.com. We're posting research updates in the form of full-length documentation, both in our GitLab and at laberation.pubpub.org for the most refined documents we have done so far. And our demo and info videos are available at youtube.com/@vulpinelabs. We can help you streamline your bioinformatics workflow if you're running a laboratory or a other research institution and you wish to know more about how we can help you out using our modules from the GESS. Then please get in touch either via Mastodon at vulpinelabs@kitsunet.net or email corp@vulpinedesigns.com. We'd love to hear from you. And thank you very much for listening. Have a good day.